Welcome to module 4. So in this module we're going to talk about forces and laws of motion. So let's start with the section. So in this module we're going to discuss first the changes in motion. Second, we're going to discuss Newton's first law. Third, we're going to talk about the Newton's second and third laws. Finally, we'll end it with everyday forces. So let's start with section 1. In section 1, so our objectives are to describe how forces affect the motion of an object. Second, to interpret and construct free body diagrams. So let's start an example with force. So what is force? So force is simply an action exerted by an object which may change the state of the object state of rest or motion. So in simple sense, so force is that which changes or tends to change the state of an object. So which means an object at rest can come into motion due to force. An object in motion can come to rest due to force. But there is also a chance that an object in rest continues to stay at rest provided the force is also being applied. So this example can be applied to, for example, let's say if you have a wall in front of you and you're trying to push that wall. So if you're trying to push that wall, so the force that is exerted by you is not sufficient enough to move the wall, but rather you're still applying some force, but that force is not sufficient enough to push that wall, provided here there is a tendency or tries to change the state of a body. So forces are also one of the main reasons to cause acceleration, and the SI unit for force is Newton. And forces can act either through a contact or a distance. So there are two types of forces in general. So we call them contact or non-contact forces. So forces can be classified into two types. So the first one is contact forces. The other is non-contact or field forces. So an example of a contact force would be to consider friction. An example of a non-contact force would be gravitation. So gravitational force is an example of a non-contact force, while friction is an example of a contact force. Friction, tension. So all of these are examples of non-contact contact forces. Gravitational force, electrical force, magnetic force, all of these are non-contact forces. So let's talk about force in general, and let's get into the topic of force diagrams. So the effect of a force depends on both the magnitude and direction. Remember that force here is a vector quantity, so which means it needs both the magnitude and direction. Now, when we dot diagrams that show the force vectors as arrows are generally called as force diagrams. So remember this, whenever we say the term force diagrams, it means that we are drawing the diagrams where we show the force vectors as arrows. Now, if these force diagrams that show only the forces acting on a single object, remember this again, the same force diagrams, when they are drawn in such a way that we are only showing the forces acting on one single object, we call that free body diagrams. So free body diagrams are force diagrams that show the only forces acting on a single object. So let's take an example of the two differences here. So this is an example where a car is trying to hit the wall. Now the forces are shown on both these objects separately, and also the ground. Now here the force diagram is only shown for the car. So this diagram that is only shown for the car is an example of a free body diagram. So a free body diagram shows only the forces acting on the object of interest. So in this case, the car. So let's take an example of how to draw these free body diagrams. Let's say we have a duck on an inclined plane. So let's consider that there is an object being dragged on an inclined plane. So let's say there is a rectangular object here that is being dragged on an inclined plane. Now for this object here, there are mainly forces that can be acted upon here. So the first one is gravitational force. Gravitational force acts perpendicularly downward, and the force that is affected by the surface acts perpendicularly upward to the surface, and you have the force that with which it is being dragged upon. So now if you draw only this body and write down all the forces as vector diagrams, so vectors, arrows. So this is an example of a force diagram. This is an example of a free body diagram. So that's the difference between a force diagram and a free body diagram. So with that in play, now let's talk about the Newton's first law. So the objectives in this section would be to explain the relationship between motion of an object and the next external force acting on an object. And second, to determine the net external force on an object. And third, to calculate the force required to bring an object into equilibrium. So let's start with Newton's first law. So what does Newton's first law state? So it states that an object stays at rest, remains at rest, and an object in motion continues in motion with constant velocity, right? Unless the object experiences a net external force. Remember that Newton's first law is basically the definition of force, meaning that force is something that tries to change the state of a body. So which means that when you have an object at rest, it tries to remain at rest. And when you have an object in motion, it tries to continue in motion with constant velocity. Now, for it to change that state, it has to experience a net external force. So in the other words, when the net external force on an object is zero, the object's acceleration is also zero. So with that in, let's talk about net force. So what does the term net force refer to here? So Newton's first law refers to the net force on an object. Remember the term net force. So the net force is the vector sum of all forces acting on the object. Now, the net force is an object that can be found by using the methods for finding the resultant vector. So we calculate the net vector of all the resultant vectors. We add up all the vectors or we subtract all the vectors. The algebraic sum of all the vectors is called as the net force. So let's take an example here and try to use this problem to understand how to determine net force. So you have the Derek leaves his physics book on the top of a drafting table that is inclined at a 35-degree angle. The free body diagram below shows the forces acting on the book. Find the net force acting on the book. So this is the free body diagram of the book, and it's shown that the force of table on the book is 18 Newton. The force of friction is 11 Newton. And the force of gravity on the book is 22 Newton. So let's take into consideration these forces now. So if we'll just draw the free body diagram here. So let's consider this is the book. So on this, first you have the force of the table on the book upward, the force of gravity perpendicularly downward, and the force of friction. Notice that here the table is striding downwards, so the friction will act in the opposite direction. So this is the force of friction. This is the force of table on the book, and this is the force of gravity. So we don't need to calculate any of these, it's already given. So force of table on the book is 18 Newton, force of friction is 11, and force of gravity on the book is 22. So these are the forces now. Now notice that they have said that this is on an inclined plane, which is 35-degree angle. So let's consider that this is the inclined plane here. So this angle here is 35 degrees. Now to resolve this, the problem that we have here is this is in the vertical direction, this is in the horizontal direction, but notice that there is an angle here and we do not know that angle. So to know that angle, let's try and imagine a triangle here. So notice that this is the inclined plane. So this inclined plane has an angle of 35 degrees. Now on this you have a book right here, and the force of gravity acts perpendicularly downwards. Now if you extend this vector here, notice that this is at 90-degree angle and this is 35 degrees. So from this we know that this angle would be, so this is 90 and 35, so this would be, so notice that the total angle in a triangle is 180 degrees, so we have to subtract 90 and 35 from that, so that will become 90 minus 35, so that would be 55 degrees, so this angle is 55 degrees. Now let's take into consideration the other vector as well. Now if you extend this vector, notice that this total angle here is 90 degrees. If that total angle is 90 degrees and this angle is 55 degrees, what would be this angle? So this angle would be 90 minus 55, which would be equal to again 35 degrees. So from this we have determined that this angle here is also 35 degrees. Now first thing we have to do is to resolve this vector, so the gravitational vector, into its vertical and horizontal components. So let's split this into the individual vectors. So we have the book right here, and you have a horizontal force, you have a vertical force. Now we have an angle, so this angle right here. So we found out that this angle here is 35 degrees, and this is 22 Newton, 18 Newton, and 11 Newton. So this 22 Newton, so what would be this vector and what would be this vector? So notice that this is the vector here and this is the adjacent angle. So when you resolve vectors, remember the one that touches the angle is f cos theta. So this is 22 cos theta and this will be 22 sin theta. Remember this from the last chapter where we talked about resolution of vectors. So the theta is 35 degrees, so this becomes 22 cos 35 and this becomes 22 sin 35. Now try to find out 22 cos 35 and 22 sin 35. So those values will be, so this will be 13 Newton, sorry, this is 18 Newton, and this will be 13 Newton. So now without drawing the 22 Newton vector, write down the vectors here. So we have the book right here. So this vector is 18 Newton, the downward vector is 18 Newton, this vector is 13 Newton, and this vector is 11 Newton. Notice the horizontal and vertical components. So what is said in the problem? So it said that it leaves his physics book and they are asking you to find out the net force acting on the book. So what would be the net force? So the net force is to consider the total horizontal force Fx and the total vertical force Fy. So the total horizontal force is going to be anything to the right is positive, anything to the left is negative. So it becomes 13 minus 11, and Fy will be, so up is positive, down is negative, so 18 minus 18. So in the horizontal the force is 2 Newton, in the vertical the force is 0 Newton. So the net force is going to be 2 Newton. Provided we have to also remember to write the angle. So 2 Newton along the inclined plane. So this along the inclined plane, the term here refers to the horizontal force. Notice that there is only horizontal force, so the net force is also going to be horizontal as well. So 2 Newton horizontal along the inclined plane. So this is how we can determine the net force acting on an object. So with this, now notice that this is positive here, so the 2 Newton is positive, so which means that the net force acting on the book here is going to be downward this way. So 2 Newton in the downward direction along the inclined plane, horizontally to the right, to the right. So this is how we can solve the problems using free body diagrams. So remember this method here, why this angle becomes 35 degrees. Notice that the total angle is 180 degrees, so we subtract to find this angle. We know that the inclined plane and this line, both of these are going to be perpendicular to each other, these four. So we want to find this angle here. So this angle is 55 degrees. So this becomes 90 minus 55, which is going to be 35 degrees again. So this is how we can determine the problem and solve the problem. Next, let's talk about inertia. So what is inertia in itself? So first law explains mainly two things. One, it explains force, and second, it also explains the term inertia. Notice the first sentence there: a body at rest remains at rest and a body in motion remains in motion. So inertia is the tendency of an object to resist being moved, or if the object is moving, to resist a change in speed or direction. So inertia is basically resistance to change in state. So inertia is the tendency of an object to remain at rest or to remain in motion without to resist the change in motion. So this is the idea here of inertia. So Newton's first law is often referred to as the law of inertia because it states basically that the absence of a net force will always preserve the inertia of a body or its state of motion. Now mass is a measure of inertia. So we can only calculate mass under the body being in a state of inertia. So next, let's take the simple example of inertia and the operation of a seat belt. Now, while the inertia causes a passenger in the car to continue moving forward as the car slows down, the inertia also causes the seat belts to lock into place. Now, as the seat is locked into place, what will happen now? The illustration basically is showing that there should be one type of shoulder harness to operate. Now, because there is one type of shoulder harness, as the person stays constant, it stays constant. Now, if there is a sudden change, if there is a sudden slowdown, so the inertia causes the larger mass under the seat to continue moving, which activates the lock on the safety belt. So this is the reason why we use seat belts. The seat belts generally are trying to preserve the inertia of the moving body. So any sudden change in the moving body is being preserved by the seat belts. That's the reason why seat belts are a good way for safety. Next, let's talk about equilibrium. Now, equilibrium is the state in which the net force as an object is zero. Remember that? So the net force, if the net force is zero, we can say that the body is under equilibrium. Now, a body under equilibrium doesn't need to be at rest. It can either be at rest or moving with a constant velocity. The only condition here is that the acceleration should be zero. Now, it doesn't mean that the vector should not be zero. So the velocity can be zero or the velocity need not be zero. But remember that whether velocity can be zero or velocity should be constant. So these are the conditions under which a body can be under equilibrium. Now, Newton's first law always tries to describe the objects in equilibrium. Now, to determine whether a body is in equilibrium, we always try to find the net force. If the net force is zero, then the body is in equilibrium. If there is a net force, a second force equal and opposite to this net force will put the body in equilibrium. For example, let's say if you have a block here, let's say if you have two friends who are fighting over a box of candies. So if both of them apply the same amount of force on opposite sides, so if they apply the same amount of force on opposite sides, then also this body is said to be under equilibrium. So this type of equilibrium is called as a dynamic equilibrium. So where the body is still being, the force is being applied upon, but there is no net movement in the body. So with that, we end the topic on Newton's first law. So try to use these questions for practice. So use the same principles that we used for the problem before. So where we try to find the net force. So pause the video right here and try to solve this problem. So if you have net force in both the x and y directions, then use the formula F net equals square root of sigma fx square plus sigma fy square. So this is the net force. How you calculate when both of them are present. If any one of them is not there, if any one of them is zero, then we can directly write F net is equal to that the one that is present there. So use the same principle, pause the video right here and try to solve this problem. So if the net force, both of them are present, then for calculating the angle, tan theta becomes sigma fy by sigma fx. So these are the two formulas to use. Now let's continue our discussion on to section 3, Newton's second and third laws. So in this section, we're going to try to describe an object's acceleration in terms of its mass and the net force acting on it. Second, we're going to try to predict the direction and magnitude of acceleration caused by a known net force. And finally, try to identify action-reaction terms. So let's start with Newton's second law. So Newton's second law states that the acceleration of an object is directly proportional to the net force acting on the object and inversely proportional to the object's mass. So acceleration A is proportional to the net force acting on it, and it's also proportional to the inverse of the mass. So combine both of them, we get sigma F by m. So from this, if you remove proportionality, then sigma F can be written as F equal to ma. So F net is equal to ma. So this is the Newton's second law of motion. So Newton's second law is generally used to solve problems that involve acceleration. So let's start with the problem here. So Robert and Laura are studying across from each other at a wide table. Laura slides a 2.2 kilogram book towards Roberto. And if the net force acting on the book is 1.6 Newton to the right, what is the book's acceleration? So the net force is already given. So F net equals 1.6 Newton to the right. So to right, it's always positive, so plus 1.6 Newton. And the mass of the book is 2.2 kilograms. So we know that F net equals ma. So we are calculating A. So A becomes F net by m. So F net is plus 1.6 Newton divided by m here is 2.2 kilograms. So what would be 1.6 divided by 2.2? So that would become 0.7272 meter per second square. So write it down as 0.73 meter per second square. So this is the acceleration of that book that is being pushed with a force of 1.6 Newton. So use the same principle now. Pause the video right here and try to solve these problems. Next, let's enter into Newton's third law. So what does Newton's third law state? So it states that if two objects interact, the magnitude of force exerted by object 1 on object 1 by object 2 is equal to the magnitude of force simultaneously exerted by object 2 on object 1. So for simple words, every action will have an equal and opposite reaction. So because these forces can coexist, either forces can be called the action or reaction. So that's why we use the term action-reaction pair to refer to the forces acting here. For example, let's say we are trying to push a nail onto, let's say we are trying to apply force on the nail into a wall, so into a wood piece. Now the force on the wood, on the nail will be outward, while the force of the hammer on the nail would be inward. Now both these forces will be equal or opposite to each other. So to drive the nail into the wood, the hammer on the nail should be higher than the wood on the nail. So that's the only case where we can find the chances that the body can go inside the wood. Now action-reaction pairs do not imply that the net force on the either object is always zero. So it basically states that they are always equal and opposite, but either object may still have a net force on it. So with that, we end the topic on Newton's second and third laws. So in the next lecture, we'll continue our discussion on everyday forces. We're going to discuss the differences between mass and weight. We're going to talk about the direction and magnitude of normal forces, and we're going to talk about air resistance as a form of friction, and finally use coefficient of friction to calculate the frictional force. So with that, we end lecture 1 of forces and laws of motion. So we'll continue everyday forces in lecture 2. I will see you again in the next.